This is the first of two video tutorials dedicated to the topic of prognostics-informed diagnostic analysis. In this video, we will look at ways in which the prognostic definitions within Express can be used to modify the analysis of a system's ability to detect faults when they occur. When calculating or evaluating fault detection, prognostic definitions within Express can be treated in three different ways. First of all, when a prognostic sequence is defined within an Express diagnostic study, then the resulting prognostic coverage will be added to the fault detection coverage to present an overall characterization of the failures that are handled by that system's PHM solution. In other words, for this approach, prognosed failures are included in the diagnostic analysis. Secondly, the prognostic coverage can be thought of as faults that will be avoided thanks to prognostics. The system's fault detection coverage will then represent the ability of diagnostics to detect faults that are not already handled via prognostics. In this case, prognosed failures are excluded from the analysis. The third option is to ignore prognostics altogether when evaluating the diagnostic performance of the system. Before we look at how this works in Express, let's look at how the fault detection numbers would be calculated for each of these three approaches. We'll use this simple 5-box design to demonstrate the differences between the three approaches. And so that the math is intuitive, we'll assume that each of the 5 boxes fail equally often. In other words, each box represents 20% of the possible system failures. Now, say that we were to have tests that could detect failures to boxes A, B, or C, but not to boxes D and E. If we ignore prognostics altogether, then the expected percentage of faults detected would be 60%, the sum of the relative failure probabilities for boxes A, B, and C. Now, let's take a look at what happens to our fault detection when we take prognostics into account. Say that we could prognose 50% of the failures to boxes A and D. Moreover, let's say that failures to box B can be prognosed 100% of the time. For this example, our overall percentage of failures prognosed would of course be 40%, the sum of the various prognosis probabilities. That's 10% each for boxes A and D and 20% for box B. Now, when we calculate fault detection using the approach that includes prognosed failures in the analysis, then our overall fault detection would be calculated by summing the probabilities for all failures that can be either diagnosed or prognosed. In this example, 70% of our faults could be expected to be covered collectively by the system's prognostic and fault detection mechanisms. Now, although this is higher than the level of detection that was achieved when prognoses were ignored, it's also misleading. Consider what we're assuming here. We're saying that half of box D's failures can be prognosed prior to failure, but they can't be diagnosed once they've failed. Although this is certainly possible, it's not likely to be the case with most prognoses. What's more likely is that prognostic development results in additional sensors that can also be used to detect failures that have already occurred. In other words, the development of prognostics is often also the development of additional diagnostics. I mention this because the occasional unscrupulous salesman claims that prognostics provide better coverage than mere diagnostics, or that the use of prognostics somehow improves diagnostics. The true value of prognostics has nothing to do with its impact upon diagnostics. Prognostics only truly improves diagnostics if it makes available additional tests and additional sensors that can be used diagnostically. Tests and sensors that may have been extremely expensive to produce, I might add, since they must not only be shown to work, but also to achieve the horizon and accuracy necessary for the system to comply with contracted prognostic requirements. In this example, however, we'll continue to consider the relatively unlikely case that half of the failures to box D can be prognosed in advance of failure, but not diagnosed after they've failed. We'll also continue with the assumption that 100% of the possible failures to box B can be prognosed with 100% accuracy. Now let's look at what happens when we exclude prognostic failures from our diagnostic analysis. With this approach, assuming that prognostics will always work as predicted, half of the failures to boxes A and D and all of the failures to box B will be avoided altogether. If we wanted to assess the expected performance of our system under diagnosis, then we would simply exclude those failures that are handled via prognostics. In this example, only 60% of our possible failures will be taken into consideration in our calculations. The first thing we need to do then is to scale the failure probabilities of the expected failures so that they add up to 100%. As you can see, objects A and D each represent 16.66, or 1/6 of our expected failures. Again, this assumes that our prognostics perform as expected. Objects C and E each represent about 1/3 of our expected failures. And once again, we calculate fault detection by adding up the covered failure probabilities. This time, the sum is 50%. In other words, if prognostics work as planned, then 50% of the failures that actually occur will be detected by system diagnostics. Now, notice that this number is lower than our original fault detection level of 60%. This is because the majority of our excluded faults, including all of the faults on object B, had been detectable. Did our diagnostics actually get worse? Not at all. The diagnostics are still capable of detecting the same faults. The difference is simply that the percentage is now calculated across a different domain, the set of actual failures, failures for which either no prognostics were developed or which escaped prognosis due to the measurement having a confidence level of less than 100%. Now let's look at this example in Express. Okay, here is the Express model for the simple example that we just discussed. There are 5 single function boxes, all of which have been assigned the same failure rate, 100 failures per million hours. To make it easier to see the differences between the 3 approaches, separate tests have been created to detect failures to objects A, B, and C. Also, prognostic tests have been created for objects A, B, and D. 2 of the 3 prognostic tests have been assigned a confidence of 50. The test that represents the prognosis of box B, however, has been assigned a confidence of 100. For this example, we've left the horizon at 0 hours, meaning that prognosis will occur some unspecified time prior to failure. Now we'll create a diagnostic study, select our detection test set on the Detection Options panel, and calculate fault detection. Because no prognostic test sets were selected on the Prognostic Options panel, prognostics will be completely ignored for this first analysis. And as you can see when you highlight the last node in the flow diagram, 60% of the system's faults can be diagnosed using these tests. And if we run the detection order report, we can see that each test will detect 20% of our expected failures, with a total of 60% detected both listed in the table and in the summary. Also notice that the aggregate failure rate, the sum of all the failure rates in the system, is 500, and that the system mean time between failures is 2,000 hours. This is what we could expect from our diagnostics if prognostics were not to be implemented. Now let's look at what happens when we include prognosed failures in our analysis. In Express, prognostic measurements are included in a diagnostic analysis anytime that they're represented in the flow diagram. To do this, we must first go to the Prognostics Options panel and select our prognostic test set. We must also make sure that the algorithm is set to include prognosed failures in diagnostic analysis. We then calculate prognostics. And because detection was already calculated, we'll be prompted as to whether we want to keep the detection order that we previously calculated or if we want to discard it and just calculate prognostics. In this case, let's retain the original detection.